Hello everyone and welcome to the lecture number 8 for the automated manufacturing. In today's lecture we are going to cover the topics that including first the manufacturing systems and automation. Before that we are going to have the cover all the following contents. First is going to start with the machining costs, manufacturing system and automation, numerical control systems, and we are going to have later some time for questions and discussions that are going to be related mainly to the final exam, and before that, the assignments. So we start first with the estimation of the machining cost. You can find some hints about this part of the lecture from the previous lecture slide, from the last week lecture slides. So the estimation of the cost, considering the cost of the machining for one item, should include the following parameters. First, the labor cost per unit time, or how many dollars per hour we are going to pay for the worker. Second, the CO, which is the overhead cost per unit time. And this once again is going to be how many dollars per hour. And the example for that is going to be the depreciation of the equipment and maintenance costs. We have also the CT, which is total cost of the tool, with TS, which is setup time, because once again, these are going to be time which is going to be included within the labor cost. The time of the machining, the TC, which is the tool changing time, the T, which is tool life, and finally total cycle time. Have the marking here, okay. Okay. Total cycle time in that case is going to be the addition of the TS plus the TM plus the TC multiplied by the time of the machining divided by the total tool life, because we're not going to change the tool for every part we are going to machine. So the cost of the components for one item are going to be identified as the material cost, which depends on the volume of the material we are going to use. The setup cost, which is going to be the CD multiplied by the TS, which is labor cost multiplied by the time of the setup. For example, you are going to put the part on the device. It's going to take you something about 2 minutes. So 2 minutes actually is going to be divided by 60 minutes. This will give you the time in hours. Then you're going to multiply it by the time, by the cost of the labor per hour. For example, it's going to be $60 every hour. So this will be the setup cost. The machining cost, which is going to be labor cost multiplied by the time of the machining. Now, if every part is going to take 30 minutes to be machined and finished, then the machining cost is going to be equal to the $60 per hour for the worker multiplied by zero point 0.5, which is the total time in hour for machining one part. Now, the tool changing cost, which is going to be equal to labor cost multiplied by the tool cost multiplied by the time required to changing one item. So it's going to be time of the machining divided by the tool life. Now, for example, the time of the machining is 30 minutes, but the tool life is going to be 3 hours. Then the TM over the T is going to be 0.5 divided by 3, and this will make it something about 0.15, 0.15 as a factor. We multiply it by the tool cost, and then multiply it by the labor cost. The overhead cost is going to be equal to the CO multiplied by the T square. And finally, tool cost is going to be equal to the CT, the tool cost, multiplied by the TM, the time of the machining, divided by the tool life. The tool cost can be further break down depending on whether the is going to be disposable insert tool or are going to be regrindable tools. Now, most of the carbide insert is going to be throw out tools. That means it's going to be used, each edge is going to be used once, then you need to throw it and get a new one. And thus the total cost is going to be the cost of the tool itself. We're not going to do any regrinding operation like what we have in the high-speed steel. The high-speed steel, the edge when it's going to be worn can be resharpened again. And that's what we call the regrind, because we are going to use a grinding machine to create a new edge. Now, the regrindable process, regrinding, is going to be actually an extra cost. So once again, for disposable tools like tungsten carbide insert, the tool cost is going to be equal to the initial cost divided by the NE, where the CD is the initial cost of the tool, and NE is number of the edges. Some of the carbide insert is going to have something like the baklava shape. In that case, going to have 8 edges because 4 on each face, and we're going to have it on the other 4 on the other face. Now, for the regrindable tools like the high-speed steel or the carbon alloys, the cost of the tool is going to be expandable equation because in that case we can do the grinding process, and the grinding cost is going to depend on the grinding time. So in that case, just give me 1 second. I found something here need to be fixed. Sorry for that. I fixed everything before we came, but still I can find that we have some small overlapping in this part. Okay, now we go back to the slide. Okay, so we said that for the integrandable, for regrindable tool, we're going to have extended equation to calculate the tool life. Now, once again, it's going to be the initial cost of the tool plus the divided by 1 plus ng, which is the number of the edges we have, how many times we can regrind the tool, plus 1, because we're always going to have a fresh uh, cutting edge when we buy the tool. So that's mean that the total number of the the total number of the useful edges is going to be 1 plus number of the grinded uh, numbers. Now the other cost we're going to add is going to be the regrindable edges, how many times we can regrind it, multiplied by the cost of the grinding, multiplied by the cost by the time of the grinding, divided by the useful number of the edges. Now, having broken down the cost into these components, the total cost of the machining of the one item is going to be equal to the material cost, the setup cost, plus the machining cost, plus the tool changing cost, plus the tool cost itself, all going to be multiplied together, multiplied by the TM divided by the T. Now, each one of these components is going to be uh, depending on individual parameters, but most of them are going to be sharing the labor cost, like the setup cost, the machining cost, the tool changing cost is all going to be including the um, labor cost. For the tool changing cost, labor cost is going to be the grinding time, the grinding cost, because we are going to have a labor who's going to be grinding the process. Now, in all machining processes, the time taken to the machine of one piece is going to be inversely proportional to the cutting speed. That's means if I'm going to cut at higher speed, the time of the machine is going to be less, and vice versa. If I'm going to cut at lower speed, the time of the machine is going to be longer. Now, the problem is that this is very easy to analyze. Okay, I said, okay, now the time taken to machine one work is going to be inversely proportional. But that doesn't mean I always going to use the higher speed because this will reduce the tool life. Okay, so just remember this concept. Reducing the tool life is going to increase the cost of the tool, which is another parameter in the cost of the machining. So in that case, you say, okay, now let's go for lower speed in that case. Now this will increase the time of the machining, and thus we are going to have an extra cost for the machining. So both statements are not going to be correct, and the best option is simply to find the optimum speed of the cutting. So we're going for a simple turning operation. The workpiece diameter is D, and the length of the cutting is going to be L. The spindle speed is N RPM, and the feed rate F is going to be in millimeter per revolution. So the speed of the cutting is going to be equal to pi multiplied by the D multiplied by the N, and the unit is going to be in meter per minute. And then the machining time is going to be given as the length of the length of the cut divided by the feed rate multiplied by the RPM. Or simply, we can analyze that to have at the end the feed rate, sorry, the end value from this equation. If we're going to rewrite down this equation, it's going to equal to the speed of the cutting divided by the pi d. Uh, well, try to substitute some of the parameters here, taking the pi d above, and we're going to have pi dl is divided by the v. Then we're going to have the parameter k is equal to the pi dl divided by the f. Now the minimum total cost is always we're going to looking for. So if I'm going to read down the equation once again, that the total cost of the machining can be expressed as a function of the cutting speed only with some constant involving the cost and the times associated with the machining processes. So once again, we can rewrite down this equation including the value for the Tm as the K over V. So you can see that we replace the Tm by the K over V in multiple locations. The tool life, as you remember from the previous equation, that we said that the V multiplied by the T up to power n is equal to a constant. So once again, we can write down the equation that the T can be replaced with another parameter, which is going to be the C over V up to power 1 over n. For the lower total cost, we are going to need to have uh, the function of the cutting time divided by the velocity should be equal to 0. For the lowest production time, like for example, I'm going to use the minimum total time, the dtt divided by dv should be equal to 0. Well, the time of the cycle time is going to be equal to the setup time, the machining time, plus the tool cost time, tool changing time, sorry. So we always going to have the dilemma of choosing what speed should be the best, and which um, uh, which one is going to actually going to reduce the cost of the machining. So you can see that in these diagrams, that's going to tell me the value of the V minimum and the V maximum we should use in our operation. The two different cutting speed variation with the time per work part. So usually the total time per piece is going to be increasing as we are going to increase the velocity. But that is going to, sorry, total time per piece is going to reduce as we are going to increase the velocity, but then it's going to start to increase. Now, why is going to be start to increase after the maximum velocity has been approached? Because the tool life is going to be increasing, as you can see here. So this curve, the one above, is equal to the addition of the other two curves. The machining time, which is going to be reduced, but the tool changing time is going to be increasing, and thus we are going to have the optimum velocity, which is the maximum velocity we are going to approach in order to reduce the cost, the time of the machining, and thus the cost of the work part. Now, for the cutting speed, regarding the cost per piece, in that case, we are going to look for the minimum velocity that's going to have the minimum cost for the machining. So the cost we are going to have here is going to be first the machining time cost, which is going to be reduced as we increase the velocity because the time of the machine is going to be reduced as we mentioned earlier. Now, the part handling time cost is going to be always constant, and the tool cost is going to be increased as we increase the velocity because we need to change the tool more frequently, and also the cost of the tool changing time is going to be increased because the time of the tool changing time is going to be increased, and thus this cost is going to be increasing accordingly. So you can see that we are going to have the optimum value, which is going to be at the bottom of this curve, which is going to give me the lowest cost of the machining with the the best velocity we are going to achieve. Now, I remember that we're supposed to have an example here, but anyway, we're going to have another one during the tutorial for this week. Now, we're going to start with something regarding to the manufacturing systems and automation. Now, in today's life, most of the machining process or most of the manufacturing processes are automated. Now, the automation is going to be including either the material handling system or the machining processes themselves. Now, what you have learned earlier, we learned about using of the CNC machines, or for example, the uh, well, it's once again going to be CNC, but it's not going to be used for the machining. But we will talk, for example, about the cutting operation using uh, the flame cutter or laser cutter or whatever the thing is. Now, once again, everything which is going to be automated is going to be how to write down a program which make the process to be work uh, by itself and for multiple times by simply reading the same code uh, continuously. Also, the most important thing that the automation, if it's going to be fixed, then we can hardly change the type of the product. But it's going to be flexible. That's when we can reprogram the machine to make a different products. So the manufacturing system can be defined as a collection of the integrated equipment, as we know, together with the human resources that perform one or more processing and or assembly operation on the starting work material, part, or set of parts. The integrated equipment will consist of the production machine, the material handling system, the processing devices, and the computer system. The manufacturing system perform the value added work on the part or the product. Because we mentioned that we take a raw material which is going to have a lower cost, and then we start to do the machining process on it to add an extra cost as a profit. The manufacturing system usually going to be a part of a larger production system. So if this will be my production system, which always going to consist of the manufacturing supporting system and the facilities. The manufacturing supporting system can include the design process, the purchasing of the material, and the manufacturing design when you are going to decide what will be the process planning for the manufacturing of the part. You will send that to the manufacturing system. The manufacturing system is going to feed the manufacturing processes and the assembly operations with the data and get some feedback. The product itself at the end of the operation is going to measure it, and the process itself also can be monitored, and this will send some information to the quality control system, which is going to compare the input with the original data came from the manufacturing support system. If any changes are going to be happen, then it's going to send a feedback to the manufacturing support system to modify the design, for example, or modify manufacturing process, and also is going to send the data to the manufacturing system itself to align the manufacturing process if there's something going on in the wrong direction. The components of the automated system is going to be mainly three parts. The parts are going to be first the power, which is required to drive the process and the control system. Also, we need to have program of instruction, which is something like the G code that we learned how to write, and we need a control system to run the process. And thus, we're going to have the process output. Now, let's try to imagine these blocks are going to be something similar to the CNC we use in the lab. We need electricity. We need a G code, and we are going to have the control system which is going to read the code and translate it into a movement for the motor. And thus we are going to have the process which is the movement of the cutting tool to perform the process operation. Power is going to be required to drive the process and the control system. The program of the instruction may also require power, and the form of the power usually is going to be electrical. We have two types of control system in any machine. It's either going to be a closed loop or it's going to be an open loop. Now, by reading these two terms, when we say an open loop, that means we don't get to have a feedback from the operation. The process is going to be going in one direction. We're going to have the input parameters to the controllers. The controller is going to move the actuator, and thus we're going to have the process, we're going to have the output variables. Now, in the closed loop, we're going to have a feedback, and thus we're going to have the feedback sensors as the additional components we're going to have for this type of the control system. Now, before we're going to do that, we need to learn about the three basic types of the automations. As we mentioned earlier, the automation can be classified into a fixed automation, the programmable automation, and we have the flexible automation. Now, usually we can consider that the programmable automation and the flexible automation are extension of each other, with of course more advantages we can have in the flexible automation. In the fixed automation, is the processing or the assembly steps and their sequences are going to be fixed by the equipment configuration. So, for example, if I'm going to have well, it's going to be, let's say, a gas cylinder drawing machine. So this machine is always going to be capable to make the same shape of the gas cylinder. It's not going to be able to change that between the processes. If it's going to be required to change the configuration of the machine to change the product, it's going to take more effort and, of course, cost to do that. We have the programmable automation where the equipment is going to be designed with the capability to change the program of the instructions to allow the production of different parts of the products. Now we're talking now about the CNC machine, the normal one. If we're going to have all the parts going to manufacture on the same machine, we need to do that by batch. We upload the code, and then we are going to manufacture, for example, 100 parts A pieces. And then we're going to stop the operation, change the setup, change the device, for example, and we're going to put a new program and we're going to manufacture another 100 parts for the parts B, and so on. And that's what we call the programmable automation. Now, for the flexible automation, it's going to be extension of the programmable automation, in which there's a virtually no loss on the production time for the setup changes or the reprogramming. What we're going to have in this case is that we're going to have something like the counter, and we are going to have all the parts going to be started up with the same startup material. For example, all the parts going to be manufactured from the same block, similar to the one we use in the lab, which is 100 by 100 by 20 millimeter thickness. So in that case, the same part is going to be using the same setup, so no need to do any changes. We're going to have a robotic arm which is going to pick the part and put in the machine instead of using the manual setup. And device is going to be electronically operated, so no need to have a worker to tighten up or loose in. And finally, what's happening is that the codes are going to be run in a different patches from time to time without need to stop and upload the code. Simple extension program can simply upload the codes for a certain time. For example, the code for the part number 1 is going to be running for the first 30 uh, uh, process. It's going to make, for example, 30 parts from the product A, and then the code will be changed, and we're going to make a 50 pieces for the product B. So the thing's going to be changing without changing any actual setups or the pre-programming for the operation. Now, fixed operation is going to have a high initial investment for a specialized equipment, high production rate because usually it's going to be linked to the mass production. The program of the instruction cannot be easily changed because it's going to be fixed by the equipment configuration. Thus, we are going to have little or no flexibility to accommodate the product variety. So in the first case, if I'm going to take a look for the variety, this will be the variety with the count of the pieces. Let's say it's going to be n. Now, in that case, we are going to have high n but low variety. We can produce too much parts, but it's always going to be one or maximum two different products. Now, for the flexible automation, for the fixed automation example, it's going to be these examples. Now we are going to have the hard or the fixed automation to make the engine blocks and the cylinder heads. So the start is going to be by insert the raw material at the beginning. Again, to do multiple forgings and multiple operation on the part until we're going to have the engine block to be ready at the end. Now, for such system, it's going to be very hard actually to change uh, the type of the product we're going to have on this manufacturing system. Now, we're coming back to the role of the programmable automation. Now, in the programmable automation, we're going to have once again high investment in the general purposes of the equipment that can be reprogrammed. The ability to cope with the product variety by the reprogramming of the equipment is suited for the patch productions because we can simply change the program after finishing the first batch of the production. And then we can change the setup, change the program, and manufacture another type of the materials or another model of the products for a certain batch. The loss of the production time is going to be for the reprogramming and the change of the physical setup for the manufacturing process. Usually, because we are going to have some loss in the production time, we are going to have lower production rates than the fixed automation system. Now, just remember that the previous one was just manufacturing the same part multiple times, and thus we're not going to have any loss in the production time. The flexible automation we said is going to be an extension of the programmable manufacturing automation system. It's going to have a high investment cost for the custom engineered equipment, capable of producing or the mixture of different parts or the products without loss of the production time for changeovers and the reprogramming. Thus, we are going to have a continuous production of different parts or the different product styles. The medium production rates between the reprogrammable time and the fixed automation. An example for the flexible automation system is going to be the sheet metal production line, which is going to use a high investment machines, which is going to have a multiple operation. Now, in this example, we're going to start all from that point. Now, this will be the aisle which is going to have the automated storage facility. Some of the stored material is going to be the finished part, and some of the stored material is going to be the raw material. So in this automated system, we're going to have a retrieval system. Take the sheet, put it on the AGV car here. The AGV car is going to take the parts between the different manufacturing processes. The shearing cell, the punching cell, or the bending cell. So for example, the product A is going to go for the shearing cell first, the punching cell second, and then go back to the storage system. The product number 2 is going to go for the punching cell first, the shearing cell second, and then the bending cell 3. So the movement of the AGV to take the part between the different machines is going to be the decision on what will be the type of the product we are going to have. So the continuous movement, the continuous operation of the production line is going to be producing a different products continuously without any stopping to change the physical setups. Now, hardware components of the automation we have. Now, because it's going to be automated, we're going to have computer. The computer need to contact with the parts and the machine. So what we are going to do is that this computer is going to use first sensors. And also we're going to need an actuators to take an action. Interface devices between the sensors, the actuators, and the control system. And we need the process controllers, which are going to be a computer-based devices such as the programmable logic controllers, or what we know as the PLCs. So we start first with the sensor. What is the sensor? It's a device that converts a physical stimulus or variables of the interest like the force or the temperatures into a more convenient physical form like the electrical voltage for the purposes of measuring the variables. Now let's have an example of the sensors before we're going to go to the two types of the sensors. Now if I'm going to have a temperature sensor is going to have a thermocouple, just a plate. When the temperature is going to be increasing, the resistance of this metal thermocouple is going to be changing. For example, it's going to be increasing. Decreasing. Thus, the amount of the electricity to be passed is going to go higher. And thus, we can read the amount of the currents to translate it into a reading in our device. So simply changing the heat, sorry for that. Okay, the heat into a useful parameter that can be read. We have two types of the sensors. We have the analog sensor, where the measurements is going to be continuous analog variables and converted into a continuous signals. And that's what we have in the thermocouples, strain gauge, and the emitters. Also, we have the discrete or the digital sensors that they produce a single signal that can have only a limited numbers of values, like what we have in the binary sensors, which only going to have two values, off and on, or 0 and 1. We also can have the digital sensors, which is going to have digital output signals and the interface to a computers. Now, the difference between both, once again, if you're going to have a thermocouple or the analog system, the reading will look like that, continuous reading. In the case of the discrete, we're going to have it as a pulses, or for example, like the on and off. So reading is either going to be 1 or it's going to be 0. Okay, so either 1 or 0. Now you can see that in this type of the sensors, we cannot go to a negative value. It's always going to be either positive or 0. For the analog system, it can go up, but also it can go down below the 0. That's the one of the good advantage of the analog systems. But still, most of the computers reading the signal as an analog or the discrete types. So discrete type or the um, digital type. So the transfer function of the sensors, the input output relationship between the input value of the physical stimulants and the output value is going to be generated by the sensor, which is going to be the value of the sense or the output of the signal we're going to have from the sensor is going to be a function of the sense item. So for example, if I'm going to have this as is going to be the temperature. So higher temperature is going to result of higher current coming out from the uh, thermocouple. The analog sensors, the relationship is going to be always as a constant, which is the value of the sensor output when the stimulus value is going to be equal to 0, and plus the m multiplied by the s, where the m is a constant proportional between the input and the output, and the s is the value of the stimulus value we have. So for example, this one is going to be the temperature. So if the temperature is 0, okay, if the temperature is 0 here, this bar is going to go to 0. We're going to have the reading a certain current, which is going to give me the reading to be equal to 0. Now, if this temperature is going to be dropped down, this value is going to be negative, okay? And thus the current is going to be measured is going to be less than the value which give me the constant 0, and thus we're going to have the reading to be negative. If it's going to be increased, then we're going to have above the current at reading the parameter 0, and thus we're going to go for the higher reading for the sensor. Now for the binary sensors, the thing is going to be quite different. The reading is going to be equal to 1 if there's anything to be sensed, and it's going to be 0 if there's an absence or negative value for the stimulus. The actuators is a device that converts a control signal into a physical action. and usually is going to be a change in the process input parameters. The action is going to be typically mechanical, such as the change in the position of the work table or the speed of the motor we have on the CNC machine. The control signal is usually going to be a low level, and an amplifier may be required to increase the power of the signal to drive the actuators. The amplifier is usually going to be electrical, hydraulic, or pneumatic. Between the actuators, the sensors, and later uh, the control system, we need to have the interface devices. The interface devices allow the process to be connected to the controller and vice versa. The sensor signals from the process are going to be fed into the controller, and the command signals from the controller are going to be sent to the process. Now, what are the types of the interface devices? Now, just remember that the reading from the sensor are going to be either digital or analog. Now, the problem is that the computer always going to read a digital values, not going to read an analogs. So that's why we need to have the interface. The interface is going to change the analog to a digital, and then for the actuators, it's going to send it from the digital to analogs. So the types of the interface device are going to be first analog to digital converters. We have the digital to analog converters. We have contact input output interface, and we have the pulse counters and the pulse generators. And actually, most of these things you are using uh, in your daily life, but without knowing that. Now, let's have an example about that. The analog to digital converter. Analog to digital converter. So we have these thermometers in every room we have in the university. So if I can to set the temperature to 24 degree, just an example, 24 degree. So the sensing is going to be analog, but the output we would like to have to stop the air conditioning system from working is going to be a digital value. So that's why we're going to have the analog to digital converter uh, in our control system we have for the air conditioning system in the room. Now we have also digital to analog converters, and in that case, after we sending after the controller is going to send the signal to drive the analog actuators or other analog devices, like for example, it's going to be the fan with a multiple speed. It's going to send the signal to start the motor, but it's going to have a different value for the speed of this motor, and that's why we need to change the digital value to an analog value. Also, we have the contact input output interface, which is going to be a communication of the binary data between the process and the controllers. We have the pulse controllers and the pulse generator. Now, it's not usually going to be happened uh, in the air conditioning system, for example. But let's talk, for example, about the CNC machine we used in the lab last week. Now, this machine was using something called the stepping motors for moving from one position to another. To move this stepping motor, the data is going to be transferred into a number of the pulses need to be moved. So the pulse is going to be sent, and thus we're going to have the steps of the motor to be moved according to this value. Or, for example, I'm going to have a conveyor belt which is going to move for a certain distance before it's going to drop the item. So the number of the turns of the motor of this conveyor belt is going to be an input as a pulses from the system. Or, for example, we're going to have a packing system which using the light sensor to check the number of the part passing through the conveyor belts. So in that case, it's going to count how many item has been passed. Or of course, this will be done by the number of the pulses of the light which has been encountered every time that the box is the part is passing through the conveyor belt. And for example, it's going to count for 25 uh, uh, counts before the box is going to be considered to be filled, and then move the box and get another one to be refilled. Now, the most important thing with all the other equipment is something like you having a human without a brain. Now, the brain in the automation system is going to be the process controllers. Most process controller systems are use some types of the digital computers as the controller. It's always going to be computers. Now, the requirement for the real-time computer control system is going to be first to respond to the incoming signals from the process, um, transmit the commands to the process, execute the certain actions at the specific points in the time, communicate with the other computers that may be connected to the process, and finally accept the inputs from the human operators. Now, one of the most uh, what they call it, the most popular um, and the most known process controllers is what we know as the programmable logical controllers. Something like a microcomputer. It doesn't have a screen most of the time. It doesn't have a fixed keyboard, but you can always connect the keyboard and the screen, or even the PC to the PLC. PLC, a microcomputer-based controller that uses the stored instruction in a programmable memory to implement the logic, the sequencing, the timing, the counting, and the arithmetic control functions through a digital or analog input-output modules for controlling the machine and the processes. Now, where will be the first example you are going to have for the PLC? It's everywhere. That's including, for example, uh, the washing machine. Now, for washing machine, they have a PLC that's using the fuzzy logic to running the operations of the washing process. Also, um, the elevators, the your car actually, your car have a PLC, and that's actually how we control, for example, the amount of the air or the amount of the fuel to be injected to the engine when you are going to be drive at different terrains. The PLC are widely used process controllers that satisfy the proceeding of the real-time controller requirements. The major components of the programmable logic controller is going to be first, and the most important one is going to be the processor. Now, the processor to work is going to need a power supply. So this will give it the energy. It's going to read and send a feedback to the memory which contain the program stored. It's going to have the input module, and we're going to have the output modules. And we're going to have a possibility of connecting a programming device to change the programs we have in the memory. So let's see how this system is working. First, we're going to have an inputs from the process. For example, the temperature, or the velocity, or the current, for example. This will be read from the sensors through the input module, and the input module is going to change the analog value to a digital value. Send it to the processor. The processor is going to read the instruction given to it by the programmer through the program stored in the memory. And then it's going to take a decision and send it to the process through the output module. Take the digital, send it to analog, and then send it to the output process, which can be, for example, if this was the temperature, this will be something like increase the fan speed. Okay, so that's how it's work. The numerical control is using the programs, and also it can use either computer, microcomputer like the PLC to achieve the numerical control of the system. So numerical control in general is a form of the programmable automation in which the mechanical actions of the piece of the equipment are going to be controlled by the program containing a coded alphanumerical data. So we talked about something, program containing a coded alphanumerical data, the G code for example. Data will present a relative positions between the workhead, which can be the cutting tool, and the work part. Numerical control operating principles is to control the motion of the workhead relative to the work part and to control the sequence of motions. The components we have for numerical control is going to be first the party program. Without the program, no numerical control. The party program will contain the detailed sets of the commands to be followed by the processing equipment. We have the machine control unit or the MCU. Is a microcomputer that stores and executes the program by converting each command into an action by the processing equipment, and usually it's going to be done by one command at a time. 3. We have the processing equipment. It's going to accomplish the sequence of the processing steps of the to transfer the cutting tool. The motion control system we have in the numerical controls are going to be either to be done as a point-to-point or as a continuous path. Now, for example, for the point-to-point, if we're going to do the drilling operation, or if I'm going to do the spot welding. Continuous path if we're going to do the milling operation, or if I'm going to do the continuous welding operation. For the point-to-point system, the workhead or the workpiece is going to be moved in a programmed location with no regards of the path taken to get to that location. So if I'm going to move the drilling head between different points, it doesn't have to follow any sequence. When the move is going to be completed, some processing action is going to be performed by the workhead, like the drilling of the hole or the spot welding. Thus, the party program will consist of a series of points location at which the operation are going to be performed. It's also called the positioning system. Now, the other type is what we know as continuous path system. In that case, we're going to have continuous, simultaneous control of more than one axis, thus controlling the path followed by the tool relative to the part. It will allow the tool to perform the process while the axes are going to be moving, and enabling the system to generate the angular surfaces, two-dimensional curves, or 3D contours in the work part. An example for that is going to be the many milling and the turning operations or the flame cutting. Sometimes we can call it the countering in the machining operations. Now to do the continuous path or the point operations, we need two types of the positioning. First is going to be the absolute positioning, and also we can have the incremental positioning. Now you remember that in the absolute positioning, all the locations are going to be defined with respect to the origin of the axis system. In the incremental positioning, the next location is going to be defined relative to the present location. Now, the positioning systems. Usually what we're going to need is going to be a motor and least screw arrangement in the numerical control positioning system. An example we're going to have here is going to be the work table for the milling machine. So remember that the cutting tool is going to be rotating and moving upward and downward along the z-axis, while the table is going to be moving along the x-axis and the y-axis. Okay, so we have the y-axis and we have the x-axis. Now in this diagram we can see that the table is going to have to be connected to a lead screw. When this lead screw is going to be rotating, the table is going to move to the left or the right along the axis of the motion. If I'm going to have the other direction to be moved, then I'm going to have the piggyback system, another system to be connected here. This screw is going to be on perpendicular to that one, and it's going to move it to the other axis. So the positioning system is going to convert the coordinates specified by numerical control part programs into relative positions and velocities between the tool and the work part. Now, how it can do that? The numerical control part program is going to be controlling the motor. The motor is going to increase the speed and rotate to, or reduce the speed and rotate a certain number of rotations. And this will send the table forward or backward at a constant speed. The least screw pitch value, where the tape or the p-value, you know that we have different types of the screw. We have the coarse one and we have the smooth one. The pitch value is how many millimeters that the screw is going to be moved in one revolution. Now you can see for the coarse screw, if you're going to turn from one revolution, it's going to go, for example, for 3 millimeters. If you're going to have the smooth one, the one revolution is only going to take it 4.5 millimeters. So that's the difference between the different types of the least screw pitch value. The table velocity is going to be what we have it as the feed rate on the machine. It's set by the number of the RPM of the least screw, or how many revolutions per minute we are going to have for the least screw. So higher RPM value is going to achieve, of course, a higher value for the feed rate. Now the feed rate is equal to the N multiplied by the rotational feed rate. So remember that equation. Then to provide the XY capability for the numerical control positioning system, a single axis system is going to be bigger packed on the top of the second perpendicular axis. The control system can be classified as an open loop control system or the closed loop control system. So you can see that the main difference between both are going to be the feedback. If we don't have feedback, it's going to be an open loop. If we're going to have a feedback, it's going to be a closed loop. So in the open loop, we don't have sensors to check how many rotation that the screw has rotated, which of course is going to control the X that the table is going to move into. So instead of that, we are going to use a stepping motor. Stepping motor is going to be multiple steps motor. It can be, for example, I'm just making an example here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one have 10 divisions. So if I would like to turn the least screw to a 20 turns, okay, if I would like to turn it to 20 turns, that's mean I going to send it, I need to have 200 steps on the motor, because each full revolution is going to be 10. That's mean the 200 divided by 10 is going to be a 20. So if I going to send, if I need to have 20 revolution for the least screw, I need to send a 20 step a pulse for the motor to make it rotate for 20 revolutions. Now in the case of the closed loop, I don't have to actually send the pulses to check how many rotation I'm going to have for the system. Instead of that, I'm going to use the servo motor, which not counting the steps, but I'm going to use DAC, which is a control system using the digital current sending, and I'm going to use a comparator. So I'm going to put the input. I'm going to operate the motor. The motor will rotating the least screw, but I need to know when to stop. Now, once again, the least screw have a certain value for the pitches. So if I would like to move for example, 200 millimeters, and the pitch value is 5 millimeters per revolution, and this will make me actually turn it for 40 times before I get to reach this distance. Now, how am I suppose that I'm going to turn it for 40 times? I'm going to use something called the optical encoder. The optical encoder is going to check how many revolutions we're going to have or even the fraction of the revolution we are going to have. So in general, the open loop system will look like that. The numerical control system is only going to send the feedback to the motors to rotate for a certain number of steps. In the closed loop system, because we're using a servo motor, we're always going to have the feedback in red to tell me how many revolutions that the system has rotated. So once again, the stepper motor, as we explained earlier, is going to have a certain number of these steps to be rotated. This one, for example, let's have only 4. That's mean a full revolution where this line is going to go back to the same position, again to need to use 4 steps. It's going to go for multiple steps. So it's going to be nice actually to read about that before you're going to come to this one. We're always going to have an angle between the steps. Okay, for example, we're going to have it here by doubling the number of the steps. The angle between the steps is going to be 45 degrees, while the angle steps between the recent one is going to be 90 degrees. Now, open loop positioning system is operating without verifying that the actual position is equal to the specified position. To tell the lead screw, we are going to use a stepping motor is going to be used, which is going to be driven by the series of the electrical pulses generated by the MCU to rotate the step angle of alpha. Alpha angle is equal to 360 degrees divided by the number of the steps we have for this motor. So if my step motor is going to have, for example, 60 steps, that's mean I'm going to have 5 degrees between the multiple steps. The AM is the angle of the motor shaft rotation, and the MP is the integer of the number of the pulses received by the motor. So if I would like to know how many, what will be the angle that my shaft is rotating, I'm going to multiply the alpha, which is the angle between the steps, multiplied by the number of the pulses I send. So if this one is once again 5 degrees, and I'm going to send 50 pulses, it's going to make one full revolution or 360 degrees. The rotational speed of the motor shaft can be determined by the frequency of the pulses sent to the motor. So the Nm, which is the RPM for the motor, is equal to 60 multiplied by the alpha multiplied by the Fp, which is the frequency, divided by 360. Now the Fp is frequency of the pulses driving the stepper motor in hertz or pulses per second. The constant 60 converts the pulses per second to a pulses per minute, and the constant 360 degree converts the degree of rotation to a full rotations. The motor shaft drives the screw that determine the position and the velocity of the work table. The connection between the motor and the DC screw usually is going to use a gear reduction to increase the position of the table movement. Now, what does the gear reduction will do? It's going to reduce the RPM but increase the torque. Now, why we need torque? Because we always going to have a cutting operation, and this requires some force for the table when it's going to be moving. So you can see now that we have two different approaches or advantages for the reduction gearbox. It's always going to reduce the RPM, so we're going to have more precision for the movement, and also it's going to add some forces when moving the table. Now the angle of rotation and the rotational speed of the lead screw are going to be reduced by this gear ratio. So the AM, or the angle of the rotation of the motor, is going to be equal to the reduction value, ratio for the gearbox multiplied by the angle of the rotation for the lead screw. Also, the RPM for the motor is going to be equal to the reduction of the gear multiplied by the RPM of the gear. The linear position of the table is going to be responsible to the rotation of the lead screw and depends on the lead screw pitch value. So once again, we said that the pitch is going to be 5 millimeter for every revolution. So more revolutions is going to lead in a further distance for the table to be moved. So the equation to calculate that is going to be the following. The x is equal to the pitch value multiplied by the angle of rotation of the lead screw, then divided by 360. So you can see from the unit, millimeter per revolution, degree for the ALS, divided by the degree per revolution, which again give you 360. The number of the pulses we send to the motor can use either of the following equation: 360 multiplied by the reduction of the gear multiplied by the distance x divided by the pitch value multiplied by alpha, or the Rg multiplied by the number of the steps we have for the motor multiplied by the angle of rotation we have for the DC screw divided by 360. Usually the x is going to be in millimeters. Now for the velocity of the work table or the feed rate in the direction of the lead screw axis can be determined as the following. The feed rate is going to be equal to the RPM value for the lead screw multiplied by the pitch value. The RPM value for the lead screw is going to be equal to 60 multiplied by the frequency divided by the number of the steps multiplied by the Rg. Finally, the pulse frequency to drive the table at the specified feed rate can be obtained from the one of the following equations. Of course, depending on the what you have and we don't have, you can rearrange this equation to find any of the unknown parameters. Now we're going to have an example for the open loop positioning. Well, I prefer again to leave this one for a separate recording because you're going to have a question in this technology in the final exam. Let's read the example before we're going to start jumping to the closed loop system. Then we're going to come back for this one. Now we have a stemming motor, has the 48 steps angle, and its output shaft is going to be coupled to a lead screw with a gear reduction of 4 to 1. That means every 4 turns of the motor shaft is going to result in 1 turn on the lead screw. The lead screw pitch value is 5 millimeters. The work table or positioning system is going to be driven by the lead screw. The table must move for a distance of 75 millimeters from its current position at the travel speed of 400 millimeters per minute. Fine. How many pulses are going to be required to move the table to the specified distance? B. The motor speed. C. The pulse frequency required to achieve the desired table. Now, before we're going to move forward, let's analyze the parameter given to us. 48 steps angle. Okay, so we have the NS is equal to 48. The shaft coupled to a lead screw with 4 to 1 gear ratio. So the Rg is 4. What we have as well, the lead screw pitch value, P. The table has moved for a distance of 75, the X. The speed of 400 millimeters per minute, we have the V. We need to find the pulses number, MV. Again, you need to find the motor speed, NM. And the pulse frequency, FP. So that's what we're going to need, and we're going to go back to this example as I mentioned later. So these are the answer steps, but again, in a separate recording, so you can use it to do your preparation for the final exam or the assignment. Now, the other type of the positioning system is going to be the closed loop. We said that the closed loop system is going to use a feedback measurement to verify that the actual position is going to be equal to the specified location. A common feedback sensor used in the numerical control and also in the numerical in the industrial robotics is going to be the optical rotary encoder. So we're going to explain the rotary optical encoder, which is going to count the pulses that the number of the angles that the lead screw is actually rotating. The equation describing the operation of the closed loop positioning system are going to be analogs to those for the open loop system. In the basic optical encoder, the angle between the slots in the disk must specify the following requirement. Alpha is equal to 360 divided by the ns. Now we're also going to have an angle, but this angle is not going to be between the steps, but it's going to be between the slots. Now let's have a look on that. Now of course this will be in degree, this will be a number, and this will be in degree. So this is how the encoder will look like. We're going to have a light source here, sending a light beam to the photocell. When the photocell is going to have a reading, it's going to give me a signal pulse. 1, 1, 1, or 0, 0, 0. We have a counter that's going to count the number of the pulses, and thus is going to tell us how many slot has been passed in the encoder. So you can see that these are the slots, and we are going to have alpha. It's going to be the angle between these slots. To find this alpha, you need to know how many slots we have. 360 divided by that, and it's going to give you the value for the alpha. For a certain angular rotation of the DC screw, the encoder generates the numbers of the pulses going to be given by the following equation. The MP is equal to the angle of the DC screw divided by alpha. Or it's going to be the angle of the rotated by the DC screw multiplied by the number of the slots divided by 360 degrees. The pulse count can be used to determine the linear x-axis position of the work table by factoring in the least screw pitch value. So the x is going to be equal to the pitch value multiplied by the number of the pulses divided by the number of the slots we have on the encoder. Or is going to be equal to the pitch value multiplied by the ALS, which is the angle rotation in degree for the lead screw, divided by 360 degrees. The feed rate at which the work table moves is going to be obtained from the frequency of the pulse train. So we are going to use the same equation. The velocity of the table or the feed rate is going to be equal to the RPM value for the DC screw multiplied by the pitch value for this DC screw. The NLS is going to be equal to 60 multiplied by the frequency divided by the number of the slots. Now another example is going to be covered in a separate video, but let's read the question again. We have the numerical control work table is driven by the closed loop positioning system, consisting of a servo motor, DC screw, and an optical encoder. Now if I didn't mention it's a closed loop system, you have to know if I'm going to read the word servo motor and the word optical encoder, that's mean we are referring to a closed loop positioning system. If we're going to set a stepping motor, then we are referring to an open loop system. Now the DC screw have the P value of 5 millimeters coupled to a motor shaft with a gear ratio of 4 to 1, so the RG is equal to 4. The optical encoder is 100 pulses per revolution of the DC screw. So we have the NS is 100. The table has been programmed to move for a distance of 75 millimeters x at the feed rate of 400 millimeters per minute dV. Now find how many pulses, MP, pulse rate, and the motor speed. Pulse rate is the FP, frequency. Okay, and the motor speed, the NM. Once again, we're going to cover the solution in a separate video. Now, we need to have a precision positioning. When we do the machining, we don't want the table to move randomly, or we don't want it to move to an unspecified distance. We always need to be sure that the distance moved by the table is what been set by the program. So we need to have a precision to have a good accuracy and good repeatability for the positioning. So the precision in the positioning is going to be to have a control resolution, accuracy, and repeatability for the movement. So control resolution of the CR is defined at the distance between the two adjacent control points in the axis of the movements. Control points are going to be location along the axis to which the work table can be directed to go to. The control resolution will depend on the electromechanical components of the positioning system. The control resolution for the open loop system is driven by the stepper motor with a gear reduction between the motor shaft and the screw is going to be given by the equation that the CR1 is equal to the pitch value divided by the number of the steps we have in the motor multiplied by the gear ratio. So the small travel distance can be controlled by this operation. For the closed loop, the CR1 is going to be the pitch value divided by the NS. So take a look at the difference between the both equation. In the open loop, we are going to consider the gear ratio, while in the second case, we're not going to consider that. Why? Because the encoder is connected directly to the shaft without any reduction gearbox. Now, the control resolution due to the computer controller depends on the smallest fraction into which the total distance to be traveled can be divided as the following. The CR2 is going to be equal to the length, which has been moved, divided by 2 to the power b minus 1. The b is the bits we have in the computers. The control resolution of the positioning system is going to be the maximum of the two values that are. The control resolution is going to be the maximum between the CR1 or the CR2, where the CR2 should be less than or equal to the CR1. Now, some statistical distribution of the mechanical errors we have. When positioning system is going to be directed to move to a given control point, the movement to that point is going to be limited by the mechanical errors. The errors usually going to be due to various inaccuracies and imperfections, such as the gear plackage, and that's very common to be happen, and the play between the lead screw and the work table, and also due to the machine deflections. They are usually going to be measured to form a normal distribution with the mean value of 0 and constant standard deviation over the axis range. So in this diagram, you can see that the control points along the linear axis, where we're going to have a portion of a linear positioning system axis indicating the control resolution, the accuracy, and the repeatability. So take a look to that diagram. You can see that this will be the distribution of the mechanical errors along the axis. So from peak to peak, from this peak to that peak, we're going to have what we call the control resolution. From desired target bottom, bottom to bottom is going to be the accuracy. It is going to be equal to half multiplied by the control resolution plus 3 sigma, where sigma is the standard deviation. Now, the repeatability of the system is going to be the 3 sigma plus minus 3 sigma. is repeatability of the system. Now the accuracy in the positioning system. We said that the accuracy is going to be the half of the control resolution plus 3 sigma. The accuracy is the maximum possible error that can occur between the desired target point and the actual position reached by the system. So once again, the calculation of the accuracy is going to be equal to the half of the control resolution that calculated from previous step plus 3 sigma, which is 3 multiplied by the standard deviation of the error distribution. Repeatability is the capability of the positioning system to return to the given control points that has been previously programmed. The repeatability of any given axis of the positioning system can be defined as the range of the mechanical errors associated with the axis. So the repeatability is going to be plus minus 3 sigma. Now just have a review about the numerical control programming system and techniques. We said that we can do the program manually by hand. We can use the computer assisted part programming or using the CAD CAM. And sometimes also we can use the manual data input. Common features we are going to have for the numerical control part programming is going to be the points, the lines, and the surfaces of the work parts must be defined relative to the numerical control axis system. So we need to identify the x and the y, find the datum point, and then we are going to find all the relationship between the points. We are going to move our cutting tool between them. So the moving of the cutting tool must be defined relative to these part features. For the computer-assisted part of programming, we said we're going to use a high level of the programming language rather than the manual coding, suited to programming for more complex shape parts. And the first numerical control part of programming language was the APT, or the Automatic Programming Tool. In the APT, we need to define the geometry of the part, then specification of the toolpath and the operation sequences is going to be done. The geometry statement of the APT is that part programmer defines the geometry of the work part by constructing its basic geometric elements such as the points, the lines, the planes, and the circles. An example for that, we can set that the P1 is going to be the point number 1, which is going to have the x value to be 25 and the y value is 150. You can make the same definition for the point number P2, point number 2, P3, P4, P5. Then you are going to make a relation between these points. For example, the L1 is going to be a line which is going to start from the point number 1 and finishing at the point number 2. That's the L1. So P1 is the point located at x25, y150. The L1 is going to be the line through the points P1 and the P2. Now also you can make an arc, and you need to define what will be the center, and the system will calculate the radius. And also we can make a circle. We can make say that we're going to have a surface which is going to be between these points. Similar statements are going to be used to define circles, cylinders, and other geometry elements. Now the APT motion statements is going to be something like you talk to the computer or talk to the control system. For example, if I would like to move between point-to-point operation, I will say go to the point number 1. Move from the current location to location P1, and the P1 has been defined by the previous APT geometry statement. Previously defined geometry elements such as the lines, the circles, and the planes are going to be used to direct control. Example for countering operation is going to be go RGT along the line number 3 past to line number 4. The dice tool to go to right RGT along the line number 3 until it's going to be pushed in just past the line number 4. The line number 4 also must be a line that intersects with the line number 3. Now the other method is going to be the manual data input, or the MDI. Is a machine operator will enter the part program into the machine. And this will use the CRT display with the graphic capability of the machine tool controllers. So in that case, the numerical control part of programming statement are going to be entered using the menu-driven procedure that requires a minimum training of the machine tool operator. The MDI does not require a staff of the numerical control part of programming. So the MDI will make it feasible for the small machine shop to implement the numerical control system. So that's it for today's lecture. As I mentioned to you again, to upload the open loop and the closed loop example in separate video later. And next week we're going to talk about the manufacturing system. We're going to cover the flexible and the hard automation, and this will be covered by chapter 34 and 35 of the fundamental of the modern manufacturing. Thank you for the listening, and sorry for the disruption we had from the motorcycle outside. It wasn't my mistake. I don't know why my the filter didn't work this time. Thank you very much, and see you later.